Assalamu alaikum. This is lecture 17 of data security and encryption, and in this lecture we are going to continue our discussion about the random bit generation using the pseudo random number generators and the true random number generators. So here are the lecture contents. We have the another pseudo random number generator, and there are two different types of pseudo random number generators for discussion in this lecture, named as linear congruential generators and Blum Shub generator. After discussion of random number generators using the pseudo randoms, we will look at the pseudo random number generations using the block cipher. And there will be pseudo random number generator using the block cipher modes. There will be two modes used in this lecture, named as output feedback mode and counter mode. Then there will be two standards such as ANSI X9.17 pseudo-random number generator and NIST counter deterministic random bit generator. So this lecture explains how a block cipher can be used to construct a pseudo-random number generator. So in this first part of the lecture, we look at two algorithms for pseudo-random number generators, named as linear congruential generator and Blum Shub generator. So linear congruential generators, at first, a widely used technique for pseudo-random generator numbers, is an algorithm first proposed by Lemmer, which is known as linear congruential method. The algorithm is parameterized as follows with four members. The first member is the number m, and it is the modulus. The modulus should be greater than 0. Then there is a number a, the multiplier, which is in the range from 0 to m. Then there is a c, which is a constant increment, which should also be in the range from 0 to m. Then we have a starting bit referred as x0. It is can be a starting value or seed, and it also ranges from 0 to the number modulus m. So the sequence of random numbers are referred as xn, and it is obtained via the following iterative equation. So to generate every new random number, you multiply the number generated in the previous round with the number a, and add a number c increment and take the modulus with the m. So if m, a, c and x0 all are integers, then this technique will produce a sequence of integers with each integer in the range from 0 to m. So for example, if we choose any number m, for example 11, all the numbers in this range will be from 0 to 11. The selection of values for A, C and M is very critical in developing a good random number generator. So for many reasons, we would like the value of M to be very large, so that there is potential for producing a long series of distinct random numbers. A common criterion is that m is nearly equal to the maximum representable non-negative integer for a given computer. So for a 32-bit computer, the value of m is equal to 2 raised to power 31 is typically chosen. So the second random number generator is Blum Shub BBS generator. So the name is because due to the authors who have proposed this algorithm. So it is a popular approach to generate secure pseudo-random numbers, and it is known as BBS generator. So it has perhaps the strongest public proof of its cryptographic strength of any purpose-built algorithm. So it is a cryptographically secure pseudo-random bit generator, and it is defined as that one that passes the next bit test if there is not a polynomial time algorithm that on input of the first k bits of an output sequence can predict k plus 1 bit with the probability significantly greater than 1 by 2. The security of BBS is stated is based on the difficulty of factoring n. So in other words, given the first k bits of the sequence, there is not a practical algorithm that can even allow you to state that the next bit will be 1 or 0 with the probability greater than 1 by 2. So for all practical purposes, the sequence is unpredictable. So for determining the security of VBS algorithm, we need to determine the number n that can be an input sequence, and we find the two prime factors named as p and q. So the procedure of this algorithm is stated as follows. So first choose two large prime numbers p and q that both have the remainder of 3 when divided by 4. So the equation states that you have to choose two numbers p and q which are logically congruent if you divide both numbers by 4 and the resulting modulus is 3. For example, the prime number 7 and 11 satisfy this requirement. For example, if you divide 7 by 4, the remainder is 3, and if you divide 11 by 4, the remainder is again 3. So the algorithm works by computing the sequence n by multiplying p and q. Therefore, we have the n here is equal to p multiplied by q. So next you have to choose a random number s such that s is relatively prime to the sequence n. This is equivalent to saying that neither p nor q is the factor of s. Therefore, the BBS generator produces a sequence of bits b of I according to the following equation. So for any initial input x of 0, you have a function which is s square, and you take the mod with the n. So initial input is fed to generate x square mod n. So to generate any next input uh, x of I, the x of I minus 1 input is squared and taken mod with the n. And to generate the final bit stream b of I, x of I is taken mod with 2, and the final most least significant bit is taken as b of I to replace in the cipher text or to use as a random number. Therefore, the least significant bit has been taken in each iteration. So this table shows an example of BBS operation. Here we have n is equal to 192,649. So which was taken from two different prime numbers p and q, and multiplying each we get the value of n. Here p was 383 and q was 503. Therefore our initial S seed is produced as 101,355. So at each round input x of I is calculated and least significant bit is taken after each round. So a popular approach to pseudo-random number generator construction is to use a symmetric block cipher as the heart of pseudo-random number generator mechanism. So for any block of plain text, a symmetric block cipher produces an output block that is apparently random. That is, there is no pattern or regularities in the cipher text that provide the information that can be used to deduce the plain text. Thus, a symmetric block cipher is a good candidate for building a pseudo-random number generator. So for that case, two approaches that use the block cipher to build pseudo-random number generators have gained a widespread acceptance. The first one is counter mode, and it is recommended by NIST SP890, ANSI standard X82 and RFC 4086. The second most widespread example is output feedback mode, and it is recommended by X982 and also RFC 4086. So this figure illustrates the two methods, and in each case the seed consists of two parts. The one is the encryption key and the second is a value V, and the V value that is updated after each block of pseudo-random function, the pseudo-random number. And thus for if you use an AES 128 bit, the seed consists of 128 bit key and 128 bit value. So in the counter case, the value of V is incremented by 1 after each iteration. So in the case of output feedback mode, the value of V is updated to equal the value of preceding pseudo random number generator block. So in both cases, pseudo-random bits are produced one block at a time. For example, AES or pseudo-random number generated bits are generated about 128 bits at each round. So if you recall the output feedback mode, the output of the encryption is fed back to the initial value to produce the next value. That means the next value is dependent on the previous input value. However, in the counter mode, the initial value is added with a randomness or nonce to generate a new value based on some key. So for the output feedback mode pseudo-random number generator, this table shows first 8 output blocks, that is equal to 1 KB 1 kilobits with 2 rough measures of security. So the second column here shows the fraction of 1 bits in each 128 bit block. So this corresponds to the one of NIST tests. The result indicates that the output is split roughly equally between 0 and 1 bits. So the third column shows the fraction of bits that match between two adjacent blocks. So you can see the number differs substantially from 0.5. So that suggests that the correlation between blocks, which could be a security weakness, is very limited. Therefore, the result shows no correlation. Similarly, this table shows the results of the same key and the value V for the counter mode. And again you can see the results are favorable and there is no or limited correlation between two subsequent blocks. So one of the strongest pseudo-random number generators is specified by ANSI X 9.70 and it employs a number of applications to use this technique, including financial security application and web PGPs. So this algorithm makes use of triple data encryption standard for encryption, and its ingredients are as follows. So it starts its cycle from input, then the key is added, and finally it produces the output. So the input is the two pseudo-random input drives the generator. One is a 64-bit representation of the current date and time, which is updated on each number generation. The other is a 64-bit seed value. This is initialized to some arbitrary value and it is updated during the generation process. Again, the keys in the triple DES are 56-bit keys, and if you're using three triple DES encryption modules, all the three keys make use of the same pair of 56-bit keys, which must be kept secret and are used only for pseudo-random number generation. So finally, the output consists of 64-bit pseudo-random numbers and a 64-bit seed value, which is again fed to the input of pseudo-random number generator. So this figure defines a pseudo-random number generator, and it defines an input value V and an encryption, decryption, encryption algorithm and number of keys and output values. So before moving forward, let us define these quantities. So the first quantity we referred here is date and time at the ith generation stage. So at beginning it can be a starting date and time. The next is the V of I is the seed value at any generation stage. The R of I is a pseudo random number generated or produced at each stage, and this is the 64-bit seed value which can be again fed to the encryption algorithm. And there are two keys, DES keys K1 and K2, which are used at each step. So EDE refers to the sequence of encrypt, decrypt and encrypt using two-key triple data encryption standard to encrypt the input X. So for two keys, the technique involves one 12-bit key and three encryption, decryption, encryption modules. and total of 9 data encryption standard encryptions. The scheme is driven by two independent inputs, the date time and the value of seed by a generator that is distinct from the pseudo-random number generator produced from the generator. Therefore, the amount of material that must be compromised by an opponent appears to be overwhelming. Even if the pseudo-random number RFI were compromised, it would be impossible to deduce the value of seed from the value of resulting pseudo number, because the additional encryption decryption algorithm operation is used to produce the next value of pseudo-random generator. The second alternative is NIST counter mode deterministic random bit generator. So pseudo-random number generator is defined NIST SP800 to 90 based on the counter mode of operations, and it is widely implemented, and it is a part of hardware random number generator implemented in all the recent Intel processor chips. So deterministic random bit generator assumes that the entropy source is available to provide the random bits, and entropy is information theoretic concept that measures the unpredictability or randomness. Therefore, the encryption algorithm used in deterministic random bit generator may be a triple data encryption standard with 3 keys, or advanced encryption standard with a key size of 128, 192, or 256 bits. So in this case, 4 parameters are associated with the algorithm. So the first one is output block length, referred as out length. So length of the output block of encryption algorithm is defined by this parameter, and in triple data encryption standard it is 64 bit by default. In AES 128 it is 128 bit, 128 bit in 192, and similarly 128 bit in the 256 bit algorithm. So that means output of each of AES can be 128 bits and DES can be 64 bits. The key length is different for each of the algorithm as described earlier. If you choose the 3 data encryption standard, 3 keys of 56 bit each will be 168 bit in total. And for each of AES we have the same size of AES as referred by the name AES 128, AES 192, and AES 256. The next parameter is of utmost importance, and it is named as seed length. The seed is a string of bits that is used as input to a deterministic random bit generator mechanism. The seed will determine a portion of internal state of the deterministic random bit generator, and its entropy must be sufficient to support the security strength of deterministic random bit generator. Therefore, seed length is equal to the length of output added with the length of key. So it is the sum of previous two values in each case. So final value is the reseed interval, and it defines the length of the encryption key. It is the maximum number of output blocks generated before updating the algorithm with the new seed. So this figure shows the true principal function that comprise the counter deterministic random bit generator. So first consider how the counter deterministic random bit generator is initialized using the initialize and update function. So as you can see, the counter block cipher mode requires both the encryption key and the input counter value V. These values are needed, and it can be chosen from random numbers or from some input clock. These values are used as a parameter for the counter mode of the operation to produce the least seed length bits. The counter mode is then XORed with the entropy source to produce the final values of key and the value of the next seed, which can be then incremented by 1 to produce the next stream of bits. However, the same key is used. So the leftmost key length bits of the seed form a new key, while the rightmost key lengths of the form produce the value of next seed. So when the values of key and V are obtained, the deterministic random bit generator enters the generate mode, and it is able to generate pseudo-random bits one output block at a time. The encryption function is iterated to generate the number of pseudo-random bits desired to produce for each round, and each iteration uses the same encryption key. However, the counter value V is incremented by 1 after each round, and it is encrypted to produce the final stream of output bits. However, to enhance the security, the number of bits generated by a pseudo-random number generator should be limited. The counter deterministic random bit generator uses the parameter reseed interval to set the limit. So during the generate phase, the reseed counter is initialized to 0 and then incremented with each iteration. So when the reseed counter reaches the reseed interval, the update function is invoked. The update function is the same as initialize function. In this update case, the key and the V values lost used by the generate function serve as input parameters to the update function. The update function then takes the seed length new bits from the entropy source and then produces the new seed key and a value. So the generate function can then resume the production of pseudo-random bits. Note that the result of update function is to change both the keys and the values V are used to generate functions. So that concludes today's lecture, and in this lecture we discussed two further random number generators named as linear congruential generators and Blum Shub generators. Then we overviewed of a block cipher stream used to produce the pseudo-random numbers, and we overview two modes named as output feedback mode for random number generations and counter deterministic random bit generator functions. So if you are interested to read more about the topic, you can read the chapter number 8 of the recommended book, or you can conduct a question and answer session. Thank you very much.